good morning. Today we are going to talk about the molecular orbital theory. Before this, we have discussed the valence bond theory. Today we will discuss the basics of molecular orbital theory and how it explains the bonding situation in different molecules. So as the name indicates, this theory explains the bonding situation in different elements with the help of the molecular orbitals. And it basically states that the atomic orbitals combine together to form molecular orbitals. And we call this approximation as the linear combination of atomic orbitals. Or, in short, we can call it LCAO approximation. So linear combination of atomic orbital is an approximation that explains how atomic orbitals combine to form molecular orbitals. And it states that the number of molecular orbitals formed as a result of the combination of atomic orbitals is exactly equal to the number of atomic orbitals that are involved in forming those molecular orbitals. So what this theory basically tells us is that atomic orbitals overlap to form new orbitals, which we call the molecular orbitals. And we will see in a moment how it happens. You know that the orbitals are defined or explained quantum mechanically through their wave functions. So we can write a wave function for an atomic orbital. So, for example, we have two atoms combining together to form a bond. So we have the atom A going to form a bond with the atom B. Now these two atoms will have their own atomic orbitals, and these orbitals are explained quantum mechanically through their wave functions. So the wave function of the orbital of A is written as psi A, and that of B is written as psi B. Now these are the wave functions of the atomic orbitals of A and B. Now, these two atoms, A and B, are going to combine together to form a bond. So it means that their orbitals or their wave functions will mix together or combine together to form new wave functions. And that new wave function will be the wave function for the molecular orbital. So what we have as a result is the formation of a new wave function, which is the combination of these two wave functions, and this is actually equal to psi A plus minus psi B. Now you can see that this wave function, which is the wave function for the molecular orbitals of the molecule AB, is a combination of the atomic orbitals or the wave functions of the atomic orbitals of A and B. And you can see a plus minus sign here. Now, this plus minus sign here indicates that these two wave functions will add together, or they might also subtract from each other. So we can have two possibilities. The first one, in which both these wave functions, they add to each other. So we can write it as psi is equal to psi A plus psi B. The other possibility is that these two wave functions subtract from each other. So we have the second wave function, the molecular wave function, that is equal to psi A minus psi B. So when they add together, it means that the two wave functions are added together and they form a new molecular orbital. And that is where we assume that we have an effective overlap of the orbitals of A and B, and we have the formation of a molecular orbital, or in other words, we can say that we have a bond formed between A and B. So this wave function here, in which the two atomic orbitals or the wave functions of the two atomic orbitals are added, is known as the bonding wave function. The second, in which these two are subtracted from each other, is written here with an asterisk indicating that it is an antibonding molecular orbital, or the wave function of an antibonding molecular orbital. So what we started with were two atomic orbitals, one belonging to A, the other belonging to P. These two atomic orbitals combine together to form molecular orbitals, and you can see we have two molecular orbitals, psi b with a small b and psi star. Psi b is the bonding molecular orbital and psi star or asterisk is the antibonding molecular orbital. And why we have these two different types of molecular orbitals is that in one case the wave functions of A and B, they add together, and in the other case we have a difference of the two. Now you see that we have the formation of two different molecular orbitals when two atomic orbitals of two atoms combine together. One is known as the bonding molecular orbital, and the second is known as the antibonding molecular orbital. The bonding molecular orbital is formed when the atomic orbitals, or the wave function of the atomic orbitals, they overlap effectively, and that is where bond formation takes place. And you know that when a bond is formed, energy of the system goes down. So that means that this bonding molecular orbital is of lower energy, and the antibonding molecular orbital is formed when the two atomic orbitals, or the wave functions of these atomic orbitals, they subtract each other. So what happens as a result is that we have a higher energy situation, and that is why this antibonding molecular orbital is of higher energy as compared to the bonding molecular orbital. Now let's see all of these orbitals on an energy scale. So we have the atomic orbital of A, that is psi A, and we have the atomic orbital of B, that is psi B. And as you know that we have two atomic orbitals, so we will have the formation of two molecular orbitals as well. We have this orbital, and then we have this orbital. So you can see on this energy scale that this orbital has a lower energy than either of the atomic orbitals as well as this orbital. This obviously is the bonding molecular orbital of this molecule that is formed now, and this is the antibonding molecular orbital of this molecule. The bonding molecular orbital is formed from the effective overlap that leads to bond formation, and that is why its energy is lower as compared to both of these atomic orbitals and as compared to the antibonding molecular orbital. So this is how these orbitals are placed on an energy scale. Now the next thing is to see the electron density within these molecular orbitals. Where would electron density lie in these molecular orbitals? So we have to see that as well. You would remember that psi indicates the molecular orbital, or psi indicates the wave function of an orbital. But to show the electronic density, or to show the probability of finding an electron, we take square of the psi. So if we take square of these wave functions, we will get the probability of finding an electron. In other words, we can then determine the electron density in a particular orbital. So coming back to that equation, which shows the bonding molecular orbital, if you take square of this equation, let me write the equation again for you. That is equal to psi b is equal to psi of A plus psi of B. If you take square of this equation, this is equal to psi b whole square, and psi a plus psi b whole square. You solve this square, this bracket, this is equal to psi a square plus psi b square. This is from your math class, plus 2 into psi a into psi b. This is equal to psi b whole square. Now when you check square of the wave function, that shows the probability of finding an electron in that particular orbital. So we have the probability of finding electron or the electron density for this bonding molecular orbital here. And this is equal to this. Now here is the square on psi a. That means the probability of finding electron on A. This is the probability of finding electron on B. And here, this term, this is 2 into psi A into psi B. This originates from the overlap of the orbitals. Now if you compare the electron density on psi B, that is the bonding molecular orbital, and the electron densities on the separate atoms A and B, you can imagine from this equation that psi B square is greater than psi A square plus psi B square. This psi bonding square is greater than the sum of these two by this factor. And that means that the probability of finding electron in this orbital is greater than the probability of finding electrons on the atoms. When we consider an electron in an atom, we say that it is revolving around one nucleus. So it's a monocentric electron. So in separate atoms A and B, we have these electrons revolving around nucleus A and nucleus B. But when these two atoms, they combine together to form a bond, to form a covalent bond, then we say that the electron density lies between the two nuclei. So both of these nuclei, A and B, can claim this electronic density. And that is because of the fact that this electron density lies somewhere between the two nuclei. It is neither concentrated on A nor on B, but it lies somewhere in between A and B. And that is where this bonding molecular orbital is formed. So it shows that the electron density now is greater in this orbital rather than around these separate nuclei A and B. Right? And this shows that we have effective overlap and an effective formation of this bonding molecular orbital, and that lowers the energy, and that is why we say that the bonding molecular orbital is of lower energy than both psi A and psi B. Let's see the other equation for the antibonding molecular orbital. So here we have the wave function for the antibonding molecular orbital, and this is equal to psi A minus psi B. If you want to know the probability of finding an electron, or you want to determine the electron density in this molecular orbital, you take square of this equation. This is equal to psi star square is equal to psi A minus psi B whole square. To solve this equation, we have psi A square plus psi B square minus 2 into psi A into psi B. And now you see that this psi star square is actually smaller than the sum of the squares of psi A and psi B. And this is smaller by a factor this. And now you can say that the probability of finding electron, or the electron density, or the charge density in this orbital is lower than on these orbitals, which means that these electrons, or the electron density, still lies somewhere near the nuclei A and B rather than in the molecular orbital, that is the psi star, the antibonding molecular orbital. So what happened here is that these orbitals have not effectively overlapped to form a bond. And that is where we say that this is actually negative or opposite of the bonding molecular orbital, and that is why it's named antibonding molecular orbital. So this is how you can differentiate between the bonding and the antibonding situations, or the bonding and antibonding molecular orbitals in a molecule. Now, there are certain conditions under which these orbitals can overlap or they cannot overlap. So there are some conditions which need to be fulfilled before we can say that orbitals can effectively overlap. Let's see what are those. So the first condition for effective overlap of two orbitals is that the energies of the two orbitals combining to form molecular orbitals must be similar. So they must have almost similar energies so as to have effective overlap. For example, if we consider bond formation between two similar atoms, any of two similar atoms, two hydrogens, two halogens, two carbons, now their electron densities will mix together, or their wave functions will overlap, or orbitals will overlap if the energies of the two orbitals are approximately equal to each other. For example, if there is bond formation between two atoms, two similar atoms, and one atom is using its 1s orbital. Now, it cannot form a bond with the 2s orbital of the second atom. It will always form a bond with the 1s orbital of that atom. If an atom is using its 2s orbital and it is going to form a bond with a similar atom, it cannot bond with the 1s orbital of that atom. It will always form a bond with the 2s orbital of the second atom, which is similar to this first atom. But this is only true for homoatomic molecules. For example, H2, Cl2, Br2. But if you have bond formation between two different elements, then we can have bond formation between two different orbitals. For example, an S can overlap with a P. Right? The second condition for effective overlap is that they must have maximum overlap so as to have a strong bond. Now, how can maximum overlap take place? If we have two orbitals, for example, if we have two p orbitals, they can have maximum overlap if their wave functions are similar. For example, we have this p orbital, and you know that it has two lobes, and we can quantum mechanically label them as plus and minus. If it is going to overlap with another p orbital head-on, like this, it will have maximum overlap if the wave functions of the overlapping lobes are similar. So this plus sign can overlap effectively with the plus sign of the second orbital. But if we have this situation, now you can see that the wave functions are opposite. And now it means that they cannot have an effective overlap. And that is where antibonding molecular orbital is formed. So in a bonding molecular orbitals, the wave functions of the overlapping orbitals would be similar, but in antibonding, their wave functions would be opposite. They will, in other words, repel each other. They will attract each other, and these two will repel each other. So as to have maximum overlap, these orbitals must have similar wave functions towards each other, and then they can effectively overlap with each other. The third condition for effective bond formation is the symmetry of orbitals. Orbitals with similar symmetries around the molecular axis can effectively overlap. For example, if we have the formation of an S and P orbital, if we have the formation of a bond between an S and a P orbital, you see that the S orbital is spherical and P orbital is dumbbell. Now, it can overlap head-on with the P orbital, but it will overlap with a P orbital that is not perpendicular to the molecular axis. If it is parallel to the molecular axis, then it will form a bond with that p orbital. For example, if the molecular axis is on z-axis, then pz will form a bond with the s orbital. Px and py will not be able to form bonds because they are perpendicular to the molecular axis. Similarly, if we have p orbitals forming bonds together, if we are going to have a sigma bond formation, they are going to overlap head-on. If we are going to have a pi bond, then they have to be parallel to each other so as to have maximum overlap sidewise to form a pi bond. So symmetries and orientations are very important for effective overlap and ultimately bond formation. Now we will discuss a simple example and explain how molecular orbitals theory can explain bond formation. We will discuss some more examples in the upcoming session. So let's see the formation of a hydrogen molecule. In a molecule of hydrogen, we have a single covalent bond between the two hydrogen atoms. Now let's see how this single covalent bond is formed between the two hydrogen atoms. So we have this hydrogen here, you can call it Ha, and you know that it has one electron in its 1s atomic orbital. If you label this hydrogen as B, you also know that it has one electron in its 1s atomic orbital. Again, if we can draw it on an energy scale, so we have Ha here with a single electron, we have Hb here with a single electron. You know that these two orbitals will have the same energy because both the single electrons in hydrogen is present in the 1s orbital. So both 1s orbitals of Ha and Hb will have similar energies. Now when these two atomic orbitals overlap with each other, they will have the formation of two molecular orbitals, a bonding molecular orbital and an antibonding molecular orbital. So this side bonding will have lower energy as compared to both the atomic orbitals, and this side star antibonding will have higher energy as compared to both the atomic orbitals of Ha and Hb. Now, as we saw in the equations, next you have to find the electronic density. Now, we have to accommodate these electrons in the molecular orbitals because we do not have the atomic orbitals anymore. We have to accommodate these electrons in the molecular orbitals. And we have a total of 2 electrons. So we have to accommodate these 2 electrons in the molecular orbitals. We have 2 molecular orbitals, one with a lower energy. So we start filling from the orbital that has lower energy, and we place both of these electrons with opposite spins in the bonding molecular orbital. We will only jump to the antibonding molecular orbital if we have extra electrons. But we do not have more electrons. We only have 2 electrons forming bonds. So both of these electrons are filled in the bonding molecular orbital of H2. The antibonding in this case is empty. So this is how you can draw the molecular orbital diagram for a hydrogen molecule. Now, how does it show that we have a single covalent bond between H2, between both the hydrogen atoms? And that is known as the bond order. We have a single covalent bond here between the 2 hydrogen atoms, and that means the bond order is 1. How do we know that the bond order is 1? How do we know that there is a single covalent bond between 2 hydrogens? How do we know that there is a double covalent bond between 2 oxygens? Or how do we know that there is a triple bond between 2 nitrogens? So this formation of single, double and triple bond is known as the bond order of a molecule. We can calculate the bond order from this molecular orbital diagram. Let's see how we can do that. Bond order basically means the number of bonds between 2 atoms, and it is calculated by taking half of the electrons present in bonding molecular orbital minus the electrons present in antibonding molecular orbital. So let's see the bond order for H2. If you remember, as I showed the molecular orbital diagram for hydrogen, you can see it here again, that both the electrons in H2 are present in the bonding molecular orbital. So the bond order for hydrogen would be electrons in bonding molecular orbital is equal to 2. You can see it here again. And the electrons in the antibonding molecular orbitals in this diagram is 0. Right? So, half into 2 minus 0 is equal to 2. This is equal to 1. So the bond order of H2 is 1. That means that there is a single covalent bond between the two hydrogen atoms in the hydrogen molecule. So these are some of the basics of molecular orbital theory, how we can form molecular orbitals, how we can determine the electron density in a molecule or in the molecular orbitals that are formed, and how we can calculate the bond order of a molecule from the molecular orbitals that are formed as a result. In the next session, we will discuss some more examples and try to explain their bonding situation through the molecular orbital theory. Thank you so much. See you next time.